Thank you very much for the lovely organizers to bring in such a beautiful place for this amazing workshop. And today I would like to share some part of paper that I wrote with my amazing set of collaborators, Chris Cousins, Craig Laurie, and Yain Lee. And it will based on slight amount of previous works that I worked with various of other collaborators, but it's been really mostly based on this. And what I will really try to discuss together today is having built a holographic gravity tools for a variety of classes of Argyres-Douglas theories. So as the title suggests, you're going to really have a holography intact. And I'm going to put it into holography in one of the strongest forms that we can really utilize. And I'm going to try to proclaim why we will be able to construct for these particular classes of conformal field theories called Argyres-Douglas theories. And it will tell us more about the conformal field theory and at the same time the new gravity theories with the new type of solutions in ADS. And there are a variety of type of holographic solutions with explicit constructions in both ADS gravity side and the conformal field theory side. And today's solution will be exactly like that, meaning it'll have very explicit CFT constructions utilizing geometry, as its conference title is Strings and Geometry. And I'll also use strings and geometry for constructing the explicit ADS gravity tool. And they will actually exhibit a lot of interesting new type of properties that we'll learn about today, which was kind of the goal of why we wanted an explicit gravity solution to start with, not just for the sake of having explicit holographic solutions of Argyres-Douglas theories. So for holography, as everyone is familiar with, the most infamous type is the very first theory constructed with 4D n=4 super Young mills, which are very nice theory that has a lot of really great properties of admitting explicit bottom-up Lagrangian. And it has its geometrization coming from utilization of the S duality so that we can get it from the 62,0 super conformal field theory on torus. Where the torus is giving rise as the explicit SL2Z S duality. And at the same time, it is famously known to have exhibition of ADS5 gravity solution coming from the type 2B string theory through explicit compactification. Now, this is very nice and all, but as the title have already suggested, I want to go slightly more beyond. And the question that I'm really want to addressing here today is that how do we then explicitly bring it to more less constrained and less symmetric theories? So I'll consider less supersymmetric solutions. And also I want to bring it down to when we lose the Lagrangian descriptions for the theory. So it'll be an explicit non-Lagrangian theories. So then the explicit question that I'm really trying to address throughout the talk is that can we systematically build holographic gravity dual theories to then 4D Argyres-Douglas superconformal field theories. It has been first addressed in this particular paper and slightly more generalized here. And today we'll be discussing most of its general form that we can try to achieve for this context. And for the explicit Argyres-Douglas theories, we can even go a step beyond and try to then understand the emergent bulk gravity geometry from all the then possible nilpotent Higgsings of these Argyres-Douglas superconformal field theories, so that individual after Higgs theories will have its own holographic dual solution, and how are going to be given rise to from the flux condition to understand such allowed nilpotent Higgsings from gravity context is the type of answer that we're going to have to actually answer this question by the end of the talk. But to first address this question, what we need to have is then how do we analyze the physical properties based on nilpotent Higgsings for the IR theory after being Higgs in the nilpotent part for a generic part of Argyres-Douglas theories. So I'm going to focus a lot of that, how to derive that very explicitly. And then I'm going to build the gravity ADS solution that will actually be shown to be mapping all the physical properties to be identical for the BPS spectrum. So as a strings and geometry, I'm going to utilize geometric toolkits. Otherwise, it would be very difficult to address this nilpotent Higgsings of Argyres-Douglas theories. And what I'm going to take is the class S construction. So that we're going to have a 62,0 superconformal field theory, and this type is type ADE. But we can take it to more generic, to ABCD type. And then from here, this is then given as the type to be on the overfold of C2 mod gamma. And from this particular one, we can take the twisted compactification on this punctured Riemann surface. The G is the genus of the Riemann surface, and N is the number of punctures. And individual punctures are then described by the puncture data. So that individually we'll have assigned one of each, and that will be given as then from the codimension 2 defect on this original 62,0 superconformal field theory. Now, then the Argyres theories that you're trying to answer, which are going to be n equals 2 superconformal field theories throughout the talk, can be analyzed with this geometric construction from class S. And how we really deal with that is that the internal manifold is a sphere with two explicit punctures. One is called regular type, and the other one is called irregular type. And the prescription is that by having this explicit data is enough to prescribe the physics of the conformal field theory by this geometry description. Let me then explain where that comes from, as that's the really critical key to then describe how nilpotent Higgsing is giving us the physical data through the IR dynamics. So this is the very crude diagram of the Riemann surface, and I put n different marked points as this orange axis, and let's call them then Z1 to Zn. And then Hitchin's system has to satisfy overall here, and that's given us these very simple equations where this is the Higgs field, it's a scalar field that's meromorphic, as it's holomorphic except on this explicit at marked points. So that in turn, this Higgs field can have poles at these marked points on this Riemann surface, and thus that's why we call it punctures. Then the different type of poles will correspond to different type of punctures. First, we call regular punctures when the Hitchin's Higgs field is describing with the leading order with a 1 over z type of the pole type description. And this will depend on explicitly the element t, so that when we're looking at the generically untwisted, which is the easiest kind, while keeping it the regular punctures, then this is explicitly parametrized by the nilpotent orbit of the type that we started with, that I'm going to call it J. So that this nilpotent orbit is really going to be then corresponding from what 60 theory with the gauge group type there that we started with. Now, upon twisting, what we get is that now this one has to change on its description, and it will be instead parametrized by something G that is subset or equivalent up to this J. And how we get this element J is that we are taking first acting on the automorphism twist, thus this is a twisted regular punctures. Then a certain subset, a subalgebra of this J will remain invariant under such an outer automorphism action, so that in turn we can take the remaining this invariant subalgebra and take its Langland's dual, then that's the one given by this J. So that in turn, then we'll be able to consider both untwisted type and the twisted type by the outer automorphism twist. And the twisted punctures have to come in groups because they have to be physically relevant to be anomaly free, so that in turn it has to globally cancel off the monodromy introduced by the automorphism twist that we acted onto. Now there's irregular punctures because if you remember, we need both regular and irregular. And that one will have a different description. It has higher order singularity for this for Higgs field and the leading order. And if you notice, unlike here, we have two additional variables that has appeared, and P and B, they're both positive. And P being 0 will then bring it back to regular punctures. So that what irregular means that this P has to be an explicit positive integer. And there's additional variable B, and that's really coming from the fact that we are dealing with different kind of the irregular puncture types. And the irregular punctures to be untwisted or twisted to be tell apart is really given by the different values of this B. So what I mean by that is this is the the ones that we're going to consider today, because I'm going to consider only classical algebras, so the type A, B, C, D. So this is the J we started with. So this is the outer automorphism. When it's 1, I'm not twisting anything. And this is the ones that we are twisting, so that in turn, we're going to get the Langland's dual of the invariant subalgebra of the J upon the outer automorphism twist. So that in here, if you look at, we are actually going to get all possible ABCD type. And for there, we can have the irregular punctures, then that's prescribed by the values of B and P. And then, so that in turn, this is then entire value that we need to prescribe the irregular punctures that we're using for the ingredient for this system. So then, in turn, what we need to really then prescribe is just given as 1 regular and 1 irregular puncture to look into our Argyres-Douglas type of the superconformal field theory with n equals 2. And if you remember, the twisted puncture can only come in groups. And since we're considering classical algebras, the only outer automorphism you're allowed to have is Z2. And that's why, in turn, you've only seen Z2 in the table today. So then we can have either both paired to be twisted into Z2, or both untwisted, and those are the only kinds that we're allowed to have. So then by denoting this regular puncture as this nilpotent orbit O, and that one I've convinced you that it's coming from parameterization of B and P is sufficient to describe it, then what we all need to have to understand this theory is given as this value, 3 different values of O, B, and P, and on top of that, the algebra either J or G, because together with this, J and G is redundant information. Since this is a more physically reasonable thing that we need to take, this is the flavor symmetry group that we're going to get in the end. We're going to take that as the main variable. So then this can be recomposited into just exactly 4 variables that it depends upon to denote this theory. And the physical properties will be entirely then described based on these. Now, what do we know about these theories at first? The first thing that we need to know is central charges A and C, because these are 4D theories. And the flavor symmetry and the flavor symmetry, the central charge of the flavor symmetry. In order to get that, then we can look into this triangle anomaly to mix the flavor currents with the R current. And then we'll get this explicit expression, so that this is depending on the element G, and that's depending on the B and P values. And there's one more value that it depends on, that is M. And when it's untwisted, that's 1, so that this factor goes away. And when it's twisted, you can get the explicit factor M to be a positive integer, which depends on the different type of algebra. And for here, these are the twisted parts, so that these are the ones that has non-1 M's, so that this will be the 4, and the other 2 is given as 2. And these are group theoretic identities you can explicitly compute. And then from here, then all we understand very well is that we have now entire flavor symmetry group G, flavor central charge coming from these explicitly. And the central charges is what we need to understand, which can be computed for maybe from the UV theory, and then do the nilpotent Higgsing to give rise to the later theory is then our hope. And before I get there, I'm going to flash up an interesting fact that when this B is exactly HG check, and that's the most easy type. And then if these P and HG check are co-prime for these two, then the flavor symmetry does not get enhanced, because here the flavor symmetry is either just given by the regular puncture or enhanced by having this value. And when this is the case, it does not get enhanced from this additional element. Now then, we can consider nilpotent Higgsing of these theories now that we understand how to prescribe physical properties for a given theory. So let's start with the most highest UV theory, because for any type, we can always have the full puncture as the fully closed nilpotent orbit, and we can order it explicitly. So that any for given O as a nilpotent orbit, can be achieved from Higgsing this particular regular puncture, is then just partially closed version of this full nilpotent orbit. And we are going to keep the irregular puncture fixed because, we don't know how to really Higgs the irregular puncture. Then the overall theory of this dPGO from the here to this theory is incredible, then entirely should be prescribed by this particular nilpotent Higgsing. So how do we get that? So first, we're starting with then flavor symmetry algebra G. And because of this, we know that there exists a moment map in the adjoint of this, this G. And let's call that then flavor symmetry algebra existing here is some subset of G. Then let's give a nilpotent vev to this moment map so that we're going to get the, this explicit nilpotent element of G. So that in turn, this IR theory will depend on the conjugacy class of this nilpotent element. So that in turn, what we get is that this is exactly coming from the nilpotent orbit that we started with, which is the only input that we have given as a nilpotent Higgsing. So then in turn, what we can determine is that the punctures and the Higgsings are really then labeled entirely by the nilpotent orbits. And from here, whatever nilpotent Higgsing we're allowed to do, or from here to continue thereon, will be entirely just given by the data of this nilpotent orbit. Then how do we deduce the IR physics coming from here? Because in the end, we need to get the full anomaly information like central charges and flavor central charges and all that coming from this theory to this based on the purely nilpotent orbit data. So succinctly, then let's try to get the IR physics just depending on this nilpotent orbit O. So then let's look at the first what we know about this nilpotent orbits, which is that it is equivalent to homomorphisms of this SU2 embedded into this group G by the Jakes and Morozov. And by denoting the image of this map as a SU2X to distinguish for the SU2R, our G will be decomposed into this and additional this F, which is a centralizer of the lobe. And that was exactly the flavor symmetry algebra that we get for the IR theory. And under this, we can get the branchings of the adjoint, which will then have the SU2X, this component, so that all the erupts will be arranged into here, and then let's call the dimension as just DL. And the rest part can be arranged with the erupts of now the individual elements of JI as the following. Then from this perspective, what do we know about the IR physics from this nilpotent Higgsing of this O? So resulting R symmetry of the resulting this IR theory is then the diagonal part of the SU2 of SU2 original R symmetry and SU2X. And on top of that, only the Nambu-Goldstone modes from the moment map will actually decouple, so that in turn, what we know in the end is that the IR anomaly should be just given entirely by the UV anomaly here, with the contribution to be taken out that's coming from the Nambu-Goldstone anomaly. And in order to do that, we'll need to then look into this Nambu-Goldstone modes that contributes to anomaly, which are the chiral fermion elements. So the chiral fermions of the Nambu-Goldstone modes will go in the representation of this, so that this is coming from the SU2 new IR R symmetry here, and that's the one on the U1R part, and that's the one that's remaining the centralizer as the flavor symmetry for the IR theory as this, that's coming from here. Then we know from the field theory that a chiral fermion transforming in a representation of a particular row contributes to the anomaly polynomial 6 form as this. So then by putting these Nambu-Goldstone fermions, which were coming in this representation, can be put into explicit computed form, and this is the computed form, which has exactly 3 contributions coming from these individually. So what we learned here is that having just pure nilpotent orbit, which is the only element from geometry we can get the full entire IR anomaly based on the UV anomaly by looking into this Nambu-Goldstone anomaly polynomial. So in the end, what we will actually get is having the UV anomaly dependence. So this is the CNA, which has a Nambu-Goldstone anomaly part that's being wadded out. And same goes here. And these are the flavor central charges that we are getting. So that in the end, the IR physics is entirely then described by looking into UV and Nambu-Goldstone coming from the nilpotent orbit O. So that in turn, we know that the anomaly of the IR theory we get, which is a generic theory of the Higgs Argyres-Douglas theory, in terms of just the UV theory, which we can compute very explicitly, and what type of nilpotent orbit that it catalogs of this particular theory, so that in turn, whatever Higgs theory we're getting of the Argyres-Douglas theory, we'll be able to compute every possible physical properties of the BPS sector. So let's do an example, because it's a lot of words. It's better to actually see how it works. So for easiness, I'm just going to take a G to be SUN. Then the nilpotent orbits of this can be then given as integer partitions. And then from here, all we needed as to determine the IR anomaly is coming from then these individual elements that we need to have other than the UV part. So we can have all the things, and this is the embedding index, which is a group theoretic property, and we can compute the number of Goldstone fermion contributions very explicitly, so that in turn we'll be able to then just describe entire IR theory that we are supposed to get. So we can actually look into all of those, and we can actually now finish the table that we started with, which is that for now any DPGO theory that we get, we can get this O as a different type of partitions that can go down to, coming from this way of writing as an integer partition for the nilpotent orbits, and this is an entire possible type we can get, and we'll be able to compute its all flavor central charges, flavor symmetry, and central charges, so that we'll get the full IR dynamics of these theory purely based on this data. Wait, right. So let's see that how we can do not just here, but also for these twisted parts. So in order to do that, if you looked here, it was C partition, so that we can now look into them, which has additional more restriction. And for those, we can get all the needed ingredients from like this JIs and then all the thinking embedding indices. Now it gets really dirty fast, because number of Goldstone fermion modes will look this dirty. But you can nevertheless compute. It's quite complicated, but you can do all that, and you can do a very similar expression to SON, which is even dirtier. But in the end, we can now just have the full expression that we need. And these central charges and the flavor central charges, along with its symmetry algebras, are the ones that it needs to be matched for the holographic dual of these theories for it to be constructed. Then now let's actually construct the holographic duals of these explicit theories. In order to do that, we're going to take the M theory embedded solution. So it will be given as the n equals 2 preserving ADS5 solutions embedded in 11D. And we're going to take as a LLM type, so that we can get the generic LLM solution satisfying to give rise to them by having it to be prescribed as these. So this is the ADS5 metric term, and these are the two internal manifolds that we're taking. And this will be then prescribed with the one that's satisfying the potential D as this total equation of S to infinity. And what LLM tells us is that if we can solve this total equation, then we'll be able to solve the whole thing, and thus we'll actually get the holographically dual ADS5 solution here. And in order to do that, we first need to now think about how we're going to map into all this different twisted outer automorphism that we have implemented in that will look kind of difficult from before. One thing we know from the gravity system is that it looks like then we need to look into different type of Z2 orbifolds to be considered in the M theory context. And there are then 4 cases we need to look into, and this is a type 2B based or understanding if you're familiar with it. And you can see that depending on whether it's acting on the R5 directly or acting on overall together, or having the pair of fixed M5 branes upon this orbifold crossing through is going to give rise to a different type of BCD of the part that we need to have to look into this explicit twisted puncture contributions to be matched onto. Now then, putting them together, we can now look into the ones that can solve this total equation, which will be then given rise by the boundary conditions that will satisfy such as line charge. So that in the end, what we need to then match between the two is that we can match the central charges between the two, and for the SC2R charge to scalars, we'll match with the moment map operator from the flavor symmetry that we looked into for the previous parts. And the flavor central charge here will be then mapped into this line charge at kinks. So this is how a line charge kind of looks like. This is for linear quiver, but to give you the idea, it's like a piecewise linear conditions, so that it's encoding really solutions of this total equation, this particular thing, by boundary conditions, so that in turn, by having solved this, we're solving the entire gravity system. An additional thing that we really started with as a second question was, can you see the nilpotent Higgsings to be matched coming from the ADS5 gravity individually? And that would be possible to have achieved. And that's given as then all the allowable Higgsings that we explicitly have deduced from geometric constraints. And from here, it will be given as something called T rules. So that it will be a flux condition. So that what it means is that only the even number of M5 branes are passing through the orbit fold, so that in turn, not every possible type of the partitions are allowed, and you can actually do the particular parts that's only allowed, and that's going to give rise to what are the allowed nilpotent Higgsings you're allowed to take. So what I really mean by that is that now we have a ADS5 gravity solution that's described by the line charge in individual cases, and where the Higgsings are allowed, so that the boundary CFT, we have looked into this explicit nilpotent Higgsings that's cataloged by the different orbits. And then from here, different orbits, then we can have it from here as a Higgsing from the T rules, and it changes onto. So that what it really means is that we can have individually satisfying ADS5 gravity duals, and in turn, we need to have then the domain walls to really allow this jump along together. So that allowable Higgsings matching to the T rule really give rise to then looking into what will be the possible emergent bulk gravity geometry. And let's look into then how we constructed the internal manifold a little bit more precisely. But what we really had was that before we had the ADS5, and these are the internal manifold. So this is effectively the S2 that carries the SU2R symmetry. And this one is the M4 manifold that's containing this kind of half spindle type of geometry, which is topologically a disk. Or this topological disk element is really the one corresponding to the irregular puncture. And this point is more dealing with the closed regular puncture element. So that in turn, it can look like the modded by Z2 element of the circle is fibered over the one that contains this half spindle. Or we can look into the more resolved picture, whereas the torus is semi-direct producted onto this particular space, coming from this half of this and the remaining part. And what's interesting about this solution is that unlike the other well-known solution from the things that we're familiar with from the Sena, those two will individually be able to parametrically shrink. In fact, this will shrink when the line on here is shrinking. And this one will shrink when the disk radius, especially this rho, is shrinking. But those two shrinking moduli does not intersect, so you cannot achieve the scale separation. But we can actually still see the parametrically shrinking of between the two different internal manifolds. So then from here, what type of things of matching that we got is a very exciting part. As we match the flavor central charge to be all possibly exact matching. And for central charges in A and C, we match it by matching the two linear relations of A and C, the 2A minus C coming from the mixed R symmetry anomaly, and the C minus A from the gravity R symmetry anomaly. And they actually shown to match beyond just the leading order when a particular condition is imposed. In fact, if you remember, for the CFT, I was saying that the flavor symmetry does not get enhanced, it's just fixed as G, when B is HG check and GCD of P and HG check is 1. And let's impose that exact same condition. What we'll see is that C minus A actually matches exactly. And 2A minus C matches at the subleading order for the UV theory, and for the every Higgsings, it matches exactly. And this is for the, so I picked explicit for SUN to actually demonstrate how it looks like. So this is the UV theory, and when we compare the central charge of 2A minus C between the CFT side and the supergravity side of the ADS, the changes is looking into it like this. And this is explicitly remaining the same, and because this is P is large, so that will be matching at the subleading order. Now let's do the Higgsing. So let's consider exactly the same thing, but let's take off this explicit element that we have. And what we get is exactly 0. What's notable here is that it's really 0, meaning it doesn't have any dependence of any of the m's. So that every time you're nilpotent Higgsing, the whatever difference we had from the first part of the UV part is remaining exactly the same, and the central charge changes does not really get changed at all, which is very exciting. And already for matching into subleading order only occurs when this condition is satisfied. So that it's kind of very interesting that looking into this condition, we go beyond just an explicit large N limit, but slightly better version of the large N limit. So to conclude, I looked into to analyze the effect of physics of the twisted punctures and irregular punctures, which are very difficult to usually do. But we could now prescribe it entirely from geometry perspective and can analyze the original, the top physics and all the IR Higgsings that we can have thereof. And we could look into all possible nilpotent Higgsings that's allowed for all possible different type of twisted and irregular punctures to be considered to give rise to them. And we found the explicit expressions of these anomalies so that it can be just described by everything from the UV and just nilpotent orbit, and we can just prescribe explicit physical properties thereupon coming thereof. Now, from CFT perspective, it is always interesting to go beyond nilpotent Higgsings and understand what are the all possible types to understand these explicit Higgs branch of the theory. And hope we are working on it in progress, and it's a lot more complicated, and hopefully we'll actually finish sometime soon. Now, for the gravity part, we saw many new features that we have not seen before. Notably, first thing was that it was matching beyond just a strict large N, so that not just the leading order, we matched it more beyond subleading, or depending on the particular type of partition, actually subleading as well. And the Higgsing part, we actually got an exact matching. And it was only possible in this very mysterious type of condition. And in fact, this condition was looked into at first because there's other type of theories that we explicitly constructed by utilizing these individual DPG theories as the building blocks to build A equals C theories, where A equals C condition for these complicated glued-in theory was only occurring when this condition is satisfied, which kind of gives a highlight. Will be very interesting to look into, especially that A equals C is very manifestly required in holographic context. And here, this A equals C is actually true without taking the large N limit. And something about beyond large N, and this looks like it's a very promising aspect to look into. We also had the partial scale separating type of solution, where individual solutions were parametrically shrinking, but their locus of shrinking actually do not intersect. And we looked into explicit extension of the ADS-CFT dictionary, as all the twisted punctures to have it as a dictionary didn't really exist, so it goes explicitly beyond the Gaioruma of the Sena works. And further on, we actually looked into to get as explicit allowed Higgsings as nilpotent Higgsings to be matched by the flux consistency condition called T-rule to get the actual rising emergent bulk geometry. Thank you for listening.